Hey, how you doing? Hi, I'm Elan Barenholtz. I am the co-director of the Machine Perception and Cognitive Robotics Lab at Florida Atlantic University.
Howdy, my name is Daniel Van Zant. I'm getting my PhD in Computational Neuroscience at Florida Atlantic University, and this guy's my advisor.
I'm kind of working on a little bit of a sort of grand thesis, which is that cognition itself is basically autoregressive generation. So what I mean by that is that the large language models, like things like ChatGPT, do this thing where they're a trained network that has learned to just produce the next token. In the case of language, it's just the next word. Typically, it's just the next word, and then after it produces the next word, it uses that to feed that in as its next input, and it builds up a larger and larger input, but does this stepwise. So it's just taking an input, producing the next token, tacking that on to the previous input, and then producing the next token again, and then just does it successively. And what we see from the large language models is this seems to actually solve language. We can get more into that if we have, as we dig in. But to me, this was a kind of epiphany that perhaps this is what cognition more broadly is. That what our brain is a trained network that has learned over the course of our lifetime and experience what is the appropriate next token, whether it's, it could be language, but it could be in other modalities as well. When we're thinking visually, we might produce the next visual image based on the images that we have thought about in the recent past. And I'm sort of going after this aggressively as kind of like prove me wrong, Occam's razor, that this might account for all of cognition, that what we're doing when we're thinking and when we're reasoning is we're really just doing next token generation. And that knowledge, and memories, and all of these things are really just the trained model. So when I say, remember yesterday when we had drinks, what you're doing there is your brain is maybe over the course of the evening when you were sleeping has integrated this information into your brain that we had this experience. And what that means, what it means to have integrated is that when I say those words, remember when we went drinking, it's going to generate that sequence of the visual sequence. Which is going to happen autoregressively, and that's what it means to remember something. And then, as I'm thinking about that, and I'm remembering that, the linguistic system will be able to gather information from that and say, yeah, oh, that's right, you got it, martini, and then the linguistic system and the visual system will sort of act in concert, and basically that synthesis is what we call cognition. So that's sort of the bold, broad claim here, that all of cognition and knowledge, representation, memory, and all that, it can ultimately be accounted for as a kind of trained network that does autoregressive generation.
Absolutely. So Elan said he's almost putting this out there as a challenge, and in some sense I'm challenging it, or at least part of it. And that's that I think a really important part of cognition, and Elan alluded to this, is knowledge. So it's things we know about the world. And I have this idea and some experiments I've done that seem to indicate this idea that knowledge has its own structure, and the structure that knowledge has is nothing like the structure that large language models have. And this is really important because not only does it mean that large language models would not be able to have knowledge in the same sense that humans do, or even animals do, but it would also explain things like hallucinations, or the fact that large language models can seem like they have split personalities, where if you get them into one kind of conversation, they'll say one thing, and if you get them into another kind of conversation, they'll say a completely different thing, which is a very inhuman thing to do, unless the person's schizophrenic or something like that. And so we can get into that a little bit deeper, but that's sort of the fundamental idea, is that knowledge has its own structure, and that you can translate some of that structure into the way large language models work, but that you lose something in doing so. The other part is that I think is important at a high level is large language models work. There's some sense where you have a computer and you have software that runs on the computer. And so I think part of what I'm saying and where I agree with Elan is that language is the computer. So language has its own processing power. Language can perform operations. Language can do really important things for cognition. But that large language models are missing the software that runs on the computer. And the software that runs on the computer is where knowledge is represented and where information is synthesized and where all sorts of interesting stuff happens.
And these are obviously good points, important points. I want to sort of address the last thing first, which is I think there's a very strong intuition most people have and would share that language isn't the whole story, of course, when we're thinking and conceptualizing. So two things to say about that. One is that the reason I was gobsmacked, and I think we all should be, by LLMs, well, besides the fact that they're just extraordinarily impressive and are doing things that I didn't see coming. The scaling laws have been the scaling has sort of solved a lot of the problems that people imagined, but they're really running only on language. That's something that's very important to reinforce. Is that leave aside multimodal models for a moment, although really I don't think that poses an actual. It's not really a counterpoint, but let's just talk about text-based only, right? Large language models just churn through linguistic data, and what they learn is just the patterns and the structure of the language itself, without any exposure to. There's nothing else in its in the corpus. There's nothing else in its data set that allows it to conceptualize beyond just the relations between words. And to me, the big surprise was that that's sufficient to do what looks like fairly broad-based linguistic reasoning. In any case, linguistic reasoning about well, call it reasoning, call it whatever you want. They are able to produce chains of thought that look very much like and really pass the smell test and the sort of the rationality test. Of soundly reasoning and responding in language. And that means language seems to contain within itself the appropriate structure for generating itself, independent of any other conceptual framework. Now, in the case of human beings, of course, language is ensconced within a broader kind of environment. And that environment includes the ability to think non-linguistically. And that I'm certainly not denying that, and I'm not claiming that language operates completely modularly. Of course it doesn't. I can describe, the black shirt you're wearing. Language didn't have linguistic knowledge about that. It had to get there somehow. But that information it ultimately ends up for the linguistic system as some sort of linguistic token, and then I believe then it just runs based on sort of its internal processes. But at the same time, when we're engaging in thought, and we're talking about abstract ideas or anything. Any time we're frankly when we're thinking, the language model is also acting in concert with other faculties, and I think this. I would call it one can be mistaken, and I'm saying on the basis of my thesis, one could be mistaken for thinking that therefore there's a completely different kind of conceptual framework that isn't captured by autoregression, because we only know autoregression works. Right now, we only really know it works for language, and we don't know that a similar kind of sort of computational framework is going to work for other kinds of thought. But the thesis is that if it works for language, it likely works for the other frameworks as well. And therefore, when we're talking about having ideas outside of just language or just out of autoregressive linguistic, like the kind of things that LLMs do, I'm saying, who says? I'm kind of making the argument, like, are you sure? Perhaps we can account for all of those things. Is it just an intuition, a very natural intuition to say, like, oh, come on, that's not all we're doing. We know about abstract concepts. And I'm like, no, we don't. What we've done is we've learned over the course of our developmental history to produce this kind of autoregressive process that appears to be doing something much more abstract, but in fact, perhaps it's closer and more concrete to the kind of rule learning, structure learning that we've done that we know the LLMs can do in the linguistic domain. Now I forgot there was the earlier point you wanted to that I wanted to return to, but I'll need you to remind me what it was, because the first point that you made. Anybody remember, Addie? What was it?
Well, before we do that, you've been using the word autoregressive a lot.
Yes,
you want to explain what that means briefly?
Okay. Well, so I kind of mentioned this before. But I should unpackage it a little bit more. It's autoregression is the process where your output serves as your next input, and so as part of your next input. So let's think about it in the context of ChatGPT, which a lot of people are very familiar with. You type in a question. Here's the question. What do you think of the idea that the brain is just an LLM, right? And there's the input is just that sequence of text. So what the LLM is going to do, whether it's ChatGPT or Gemini, it doesn't matter. They all operate based on this same basic principle. It's going to say, given that string, what do you think of it's going to produce just a single token. Let's say the next thing is I think, or as an LLM, whatever it's going to say, it's just going to produce that very next token. Let's say it's right? It's, as an LLM, it often says things like that. And so that as is now going to be tacked on to the previous sequence, which is the entire question. There could be some invisible to the user kind of other tokens that are in there that shows sort of this is where the user stopped and this is where the LLM started, but it's taking in that next token that it generated, it's feeding it as the input, and it's going to say as, okay, given the previous sequence and the word as, what's the next word? And it's going to say as n, and then it'll continue to do that successively. And that's thinking. For the LLM, that's the only kind of thinking it can do, but turns out that is sufficient to be able to not only do next token prediction based on the previous 5, 10 tokens, but with a large enough context, as it's called, meaning the size of the input, basically that's getting churned through on each successive generation. It can think about things, concepts or whatever, tokens anyway, let's just be concrete, that has occurred very far in the past. You could give a document that's many paragraphs long. You could give it an entire, some of them, if the context is large enough, you can give it an entire volume, a book-sized volume. And what it's doing is it's guessing this very next token based on taking into account something that was, many chapters ago. And that's what we as humans do all the time. In this conversation, when I'm making reference now to the comments that Daniel made, I just failed at that, by the way. I was not able to retrieve. There's some sort of decay that happened there or something like that. But I'm taking into account things that have been said throughout this whole conversation. But I'm doing it at this discrete, and again, this autoregressive, it's just this discrete next token prediction. And so the power of that ability to do next token and then just do that successively is what I find astonishing, but seems to be able to reason and to conceptualize far beyond what I would have assumed just based on that simple kind of process. And so that's really autoregressive. Now, autoregression, again, it could apply to something else. Let's say I'm thinking about what I did this morning or something. Like I'm thinking about, first I had to go on my computer, and then I got on the phone and I was coordinating with these guys, and as I'm doing that, I have the experience of kind of going through a temporal sequence. And the idea is that you could probably model that same, just like in the language context. What I'm doing is I'm taking the previous input. So here's, in my mind, I'm thinking of all the events that took place up to this point, and then I'm remembering by, what was remembering means in this case is just generating that next token, and then I got my phone and I'm doing the same thing. So that would be sort of writ large. What autoregression would mean is that what you're doing is constantly just generating sort of the next slice of time or of linguistic token. This would be kind of visual tokens in the visual case, and then you're just tacking that on again to the input, and the input is just growing larger. Now, in the case of people, I don't think what we do is similar to LLMs. It's clear that there's some sort of decay function or something like that. large language models take literally the entire sequence and ram it through again and again. Very, very inefficient in some ways. Without getting too much into details, every time you do that, you literally have to process every single word relative to every single word, which is a very computationally expensive thing to do. The GPUs, the compute power is there, although it's not. Probably, it's not efficient to the point where, ask OpenAI, they're not making money.
Nobody is, I don't think.
Correct, and it's too computationally expensive. But in principle, it's sort of, I think it captures the essence of what we do. And in humans, it's clear that we don't retain the entire, I don't remember what I said, really, the verbatim, even 30 seconds ago. But some version of that, where we're somehow capturing, it's probably transformed in some way, but it's still probably this basic autoregression. So that's the core idea of what autoregression is, and what I'm proposing accounts for all of it, for cognition. And so knowledge in this case isn't organized in any way that's not captured by the representation, the pattern of how brief tokens have appeared together, I guess you could say. So I don't know what your conception of knowledge is, and I'll hand over the mic to you. But yeah, the Occam's razor challenge here is, given that knowledge in the case of LLMs is just the ability to produce the next token in such a way that they sure sound as if they know a lot of stuff, right? And there's nothing else in there but just the representation of the relations between words, and it gets very semantic as you get deeper into the network. It's not, we can't just talk about like literally relations between words. It's much richer than that. The representation of these words is a very rich thing, but fundamentally that's sort of the claim. It's not more organized than what the LLMs are doing. It's not organized in a very different way.
Yeah, I see what you're saying. So I think that's actually a great segue into the first point that you asked about, and what I wanted to talk about. So I mentioned, I think knowledge is software, and
software. That's
software that runs on a computer that we would call language. And so language isn't the whole story. And in particular, something I want to mention really quickly that I was thinking about when you talked about is, I think a strength to your point, and maybe something you should start mentioning, is language isn't the only autoregressive process that generative AI and humans share. I would say that producing images is also an autoregressive process for both.
So I did say that.
Oh, you did say that.
I made that claim. I just said
I think it's worth mentioning that humans generate images autoregressively, where they draw out like a rough sketch and then they fill in the details.
Interesting. Okay, not just speculation. I see what you're saying. That when people do actual image generation, they sort of do it autoregressively.
And when people draw a picture, they do it autoregressively. And when the image generation models that exist draw a picture, they do it autoregressively, where they kind of, it's different, but they kind of make a rough sketch and they fill in the details.
So diffusion, okay. So I was gonna, when I think of imagery, I'm thinking of like I think all of our imagery is video generation, right? We don't really do image generation as humans in our mind. Now we have to do it when we're drawing. But when I alluded to earlier, but it's more of a conjecture, is that I think our visual thinking, like a memory, episodic memory, I think could be accounted for as a kind of autoregressive video generation. Similarly, visual reasoning, like thinking about how do I get from this point to that point, I think if it takes time for us to do it, like cognitively, my suspicion is that what we're doing is just this. That's why you can't do it instantaneously. There's certain things you can just solve, like in moment of insight, recognition. Boom, I've done it. Where some things we have to think. When we're thinking, what are we doing? And so my suspicion is that what we're doing is we are actually doing this sequential autoregression. Now, I think that the video generation models. I'm not well versed enough to know if to what extent the industry is homogeneous at this point, but I know that many of them do use autoregression, and that would be essentially the same idea. Produce a frame, take into account the previous frames, like start from this point, then produce the next frame, then take the previous 2 frames, produce the 3rd frame, and so on. And that's classic autoregression. And I think that is very likely the same exact sequence that's happening when we do visual reasoning. Now, your point about when people do it, like sort of actually generate in the world, our actions are also in this way kind of autoregressive. When we're reaching for an object, and it might become, I don't want it to, it can border on the tautological, and you have to be careful. I'm making a very specific claim that the computational process really takes into account previous states, and that those are used to generate the next state. When you're reaching for something, it might not be autoregressive in this way, but but it very well might be. I haven't been able to delve deeply enough into it, but certainly when we're acting and when we're generating, we're doing it sequentially. It's certainly true, but the world operates this way. Like sequentialism is sort of built in, like it or not. One moment follows the next.
Yeah.
It's just how it's physics. It's like with the world, whatever. I'm not going to get into we're not going to go too deep here, but the world sort of unfolds and over time, for lack of a better word. And of course sequentiality is there, but there's a sharper point here about the computational process as to whether it's autoregressive. Really, it's building up a longer stack of increasingly larger input that then forms to do the next to form the next output. So I don't know if I could point to your example as necessarily supporting it, because it might be that's really just happening. To use the Markovian, it's like, is it taking the past into consideration or not? Autoregression absolutely has to take the past into consideration. Markovian processes do not. It could just be the current state is sufficient to generate the next state, and I don't know if drawing necessarily requires that you've taken the previous states. The world takes care of that. The world is encapsulated, by the virtue of the fact that you've made marks on the paper. Now you've got, instead of just a little point, you've got a curve, right? But that could just be the next curve. That's not part of your cognitive process that's taken into consideration. It's the world is changed. It's similar to cellular automata, which in some ways sort of seems autoregressive, but it's not, because the rules just say, given the state now. They're totally Markovian. The state of the environment in the cellular automata case is keeping track of the past, such that the world sort of takes care of the maintenance of, and so it's sort of in totality you get sort of autoregression, sort of strangely enough, but it's not. Computationally, in terms of the rules for generation, it's not autoregressive.
Would you say that in cellular automata, the autoregression is an emergent property that comes from the local properties of the cellular automata?
Plus the environment.
Plus the
environment, which has its memory, right? The environment has its memory of sort of what the changes take place are preserved, and that defines the state for the cellular automata. So any sort of state is, it's just I guess it's a finite, not even a finite state machine. I don't know how to forget jargon, right? Especially if you don't know if you're using it correctly. But it's just the rules are only taken into consideration. You don't ask what happened in the past. In a cellular automaton, you don't. The rules do not ask what happened in the past. In a autoregressive generative model, it very much inherently does. But just by virtue of the input. In some ways it's not that different, and I've been thinking about this, but shouldn't do this on camera. But one is sort of an internal process where you're building up this. The state is just this increasingly accumulative situation, and one is it's the world that's doing that. So they have certain very strong similarities.
So you're saying that an autoregressive process has to account for multiple states. It can't just account for the previous state. That would be a Markovian process.
It needs an increasingly it's just that the state itself is dependent on its own outputs in such a way that and it's sequential. This is very essential. So this is the big difference, right? So in a cellular automaton, there's no record in the world as to how it got there. So right now you've just got, and I don't know if we haven't explained what cellular automaton is, but let's let the listeners, just look it up, because
just look up game of life. Really cool.
Yeah. So a cellular automaton is basically it's a process for taking some simple rules that say, let's say you have a grid, and a grid can be made up of little squares, and the squares could either be black or white. And then what you do is you have a rule given. So for a given square, you say, okay, what's going on in the surrounding squares? That's going to determine an update. There's an update rule that says, given, okay, let's say I'm surrounded by black squares, I'm going to turn black, or I'm surrounded by black squares, I'm going to turn white. And basically, what happens in cellular automata is you have those rules, and then you do this for a complex grid with whatever pattern, and then interesting things happen, and it evolves. And so you can get, for example, certain kinds of patterns that recur, and certain set of stabilities that can emerge as you run this thing. And the point I'm making is, so there's a certain sense in which it's like the past leads to the present, and it's certainly the case that the environment is doing this kind of evolution. But first of all, in the computation itself, the rules do not specify what happened 3 moments ago. It's just whatever happened, whatever is the situation right now, here's what we're going to do next. In the case of large language models, the sequentiality is built in, the input that we keep feeding. So let me just back up. So the input in the case of cellular automata is the current status of the grid. The input in the case of LLMs is the previous sequence, including whatever I've generated that's tacked on most recently. Now, so these could seem very similar. Like we've got the past led to the current existence of this grid, and the past led to the current sequence. But the difference is, and this is absolutely fundamental, is that in the case of language models, the order in which those words was produced is preserved in the current environment, the current input. Whereas in the case of the cellular automata, the order is not preserved. It's just the current state. How did we get here? And that's what makes it really Markovian. There's no information about the past that's built in to the current state. Whereas inherently, in the case of language models, the input contains all of the history about the past and the previous states. So that's really a certain sense in which there's these autoregressive things, they're different. Then the environment, when the environment keeps track, that's not the same thing. The environment doesn't keep track of the entire sequence that happened. It's just really just the present. And the claim is that what we're doing, what our brains are doing, is we have to retain a history, a sequential history, in order to do the next thing.
I see. And so I think this is good in specifying where I'm disagreeing with you.
Yeah, that's what I'm hoping to get to that. I'm sorry.
Yeah. No. This has all been good discussion, but where I disagree with you is that autoregression is all that there is, and there's just sort of the entire history with maybe some decay function to draw things out, fed in, and then we generate things, and that's how.
That's in a nutshell. In a nutshell, that's there you go.
And so I think, and my view is actually the conservative one, which is funny with you being the advisor and older scientist and me being the younger scientist, but my view is the more conservative one, and it's that there's two systems here, and these two systems are very similar to what a lot of cognitive scientists have thought for a long time, which is that you have
That's how I know you're wrong. No, I'm kidding.
Which is that you have long-term memory and short-term memory, or working memory, and these are two separate processes, and in some sense, short-term memory operates on long-term memory. I think where Elan's absolutely right is that autoregression is the core mechanism for working memory, or sort of cognitive functioning, or whatever you want to call it, the things that go on in your prefrontal cortex.
I think they go on, in working memory seems to be kind of broadly distributed, like,
well,
when you think, it's not, prefrontal maybe, well, it's controversial as to how if there's like a coordination. But let's leave that aside.
It's a nice abstraction to say this process happens here, even though it's not true. So we should be clear.
Good.
Neuroanatomy is, there's this, one of my favorite papers is called Functional Neuroanatomy is Modern Phrenology. and let's be clear that that's very
Don't
true.
get me started.
But I think when you're trying to simplify things, it's still really useful to say this thing happens here and this thing happens here and then this thing moves this information from
It
here.
raises my blood pressure a little bit, but okay.
We'll talk about things with that way, knowing that that's not how the actual brain works, and there's lots and lots of issues with that. But it's a useful abstraction, I think, and maybe that's why it's stuck around for so long.
Yes, good point, right? If it's sticky, then maybe it's useful. Okay.
Yeah. I mean, if it's not, what is it? I had a mathematician who always used to say, well, this is how the universe works, and then he would say, well, if it isn't true, at least it's useful. So if it isn't
Correct.
true, at least it's useful.
Or it's leading us down the wrong path. But anyway.
At any rate.
String theorists in the comments. I do have a comment though on
Yeah, shoot.
experientially, right? I mean, it's interesting that an idea pops out to you, or a thought pops out of somewhere.
Yes.
You're not actively thinking about the thing, and it pops out. And I wonder if you wanted to.
And that would seem to be like sort of a challenge to my perspective, right? It seems completely unpredicted. It doesn't seem like the previous tokens would generate that. But my argument would be like, says who? If you'd spend some time with LLMs, you can find that they can surprise you. I wouldn't have gone off on that tangent necessarily. It goes off on a sort of a tangent that I wouldn't have said that would be the next token I would have generated. And I think the richness, what we've seen, what we know now is that the richness of the autoregressive process is extraordinary. And maybe, if you're taking in totality all of the, and we're also adding, by the way, not just linguistic, when you have that thought that comes from nowhere, it seems to come from nowhere, there are other processes that might be going on at the same time as just your sort of like thinking out loud or thinking in loud, whatever you call it, like thinking to your within your brain linguistically, but you're also thinking visually, like the predictiveness, it's very hard for us from a metacognition standpoint to be able to say that insight came out of nowhere. There's some other process the argument would be like, says who? Maybe it is predicted in some way, in ways that we're just not able at a metacognition cognitive level able to be able to grasp. But that doesn't mean it's not the same process. I don't think that's a fair conclusion. What do you think?
So what I think is that there's two things, and there's working memory, which I think you're absolutely right. I think it's autoregression, but I think there's this other thing. I think there's this other thing that's long-term memory, and there's a few reasons that it's important if long-term memory isn't anything like large language models. But let me give an example of what I'm talking about and how I'm thinking about things. So there were two people who have been going to my church and in my friend group for years that were siblings, and I didn't realize they were siblings. Mm-hmm. And so I had talked to one of them, and he briefly mentioned that his sister also goes to this church, whatever. I didn't think much of it. I don't know everyone. I was like, okay, his sister also goes to this church. These two people look similar to each other, but people look similar to each other all the time. That doesn't mean much. And then I was talking to this girl, and she said, oh yeah, my brother goes to this church. And in that moment,
clicked.
I had three facts in my long-term memory.
Yeah. I
had the fact that his sister goes to this church. I had the fact that they look similar to each other, and all of a sudden I have the fact that her brother goes to this church. And so how I want to imagine things is those are three facts, and I imagine they're stored in something like language, maybe language with a graph over the top of it and connections between them. And when I had those three facts together, I asked her, oh, is your brother this other person? And the reason I asked that is because, like you said, it clicked. And how I'm imagining things is through some mechanism, these three things got loaded into the autoregressive process. Mm-hmm. Through some mechanism that I think is somewhat separate from the autoregressive process, but these three things got loaded into my autoregressive process. My autoregressive process was able to make a relatively small jump in reasoning about it at that point. And then what's really interesting thing is the autoregressive process changed my long-term memory because I loaded in three things it generated a new thing, and then all 4 things got loaded back into my long-term memory. She looks similar to him. She has a brother that goes to this church. He has a sister that goes to this church. They are siblings.
And so you sort of updated your memory.
Yeah,
like in obviously sort of a structural way that you feel like wouldn't be well captured by whatever it is that these neural networks are learning by virtue of churning through this data and learning to do ultimately next token.
Absolutely, and the reason I think it's interesting to talk in specifics about the reason I feel like it wouldn't be well captured. So I feel like the whole system is something like what we call a graph, and a graph is essentially you have nodes and you have what are called edges, and you have this thing, and then there's an arrow pointing from this thing to this thing, and that means that this thing affects this thing, and
in one
this
direction,
thing affects this thing, one direction, right? Yeah.
Mm-hmm.
And so what I talked about is a great example of this, where I have 3 pieces of knowledge, and kind of how I think of how that's stored in long-term memory is almost as a graph, where all of a sudden I have arrows from these 3 separate pieces of knowledge to this new piece of knowledge that I created with my autoregressive linguistic process. And then I go and store that back in working memory, and we can imagine these pieces of knowledge are connected to a host of other things, and so I mentioned, they both go to my church, so that's connected to a whole other body of knowledge about who are the people that go to this church, and who is the pastor of this church, and where is the church in space, and all sorts of other things.
Right.
And there's all these arrows pointing from all of these sort of small beliefs to other beliefs. And this is really important if this is a graph, because one way to think of large language models is that they're a hyperdimensional space. So I'll get into what I mean by that. Essentially, there's something you can do with a lot of things that's called embedding, where you take something that's structured in one mathematical way and you put it into a different mathematical structure. So everybody's seen a map of the world. Everybody's seen a globe. A map of the world does not look like a globe. It's flat. It distorts certain things because you have to if you're going to flatten out a sphere. But one way to imagine that is that you are embedding a sphere into a flat plane. And so you're sort of translating each location on that sphere to a location on the flat plane. And you can still perform a lot of operations that you could perform on a sphere. So you could say, these things are this far apart and these things are this far apart, and you don't need the sphere anymore. You've embedded it. So there's 2 types of ways to embed things. There's what's called lossless. So that means I can do everything perfectly just as well as I was able to. And then there's what's called lossy embedding. So I mentioned that the distances change if you turn a sphere into a flat map, at least the normal maps. There's special maps that are weird shaped and you can perfectly preserve distance with, but the map you've probably seen, the distances are changed. So
unless you know what the original transformation was, the information is actually lost. The distance,
yeah.
the original information is lost.
And if you want to get a ruler, you can sort of measure, here's this location, here's this location, and usually the way flat maps work is it'll work on a small scale, but if you try to do like, here's California to Iceland, and here's California to Germany, it'll be way off.
Here's how big Greenland is.
Yeah, and so exactly. So this is lossy, and you can also embed the kind of structure I'm talking about, which are graphs, into hyperdimensional space, which are the type of structure that neural networks are based on. So neural networks are a series of transformations in hyperdimensional space. I won't get too into sort of what hyperdimensional space is, because that's another conversation, but just imagine graphs are a sphere, hyperdimensional space is a flat map, and to translate one into the other, you have to lose information. And actually, if the graph is very complex, you have to lose quite a bit of information. And so the case I'm making is that the knowledge capabilities, so like if you go into an LLM and say the cat is the opposite of A, the LLM will say a dog, and that appears to be knowledge. I would say that the knowledge capabilities that we see are the large language model having a lossy version of the kind of knowledge graph I'm talking about in its hyperdimensional space. But because it's lossy, we also see these kinds of issues at the edges, the same way I mentioned where if you're using a map normally and saying, how do I get from Florida to North Carolina, it's going to be fine to just look at the distance with the ruler, but if you're trying to do other things with it, it'll fail. If you try to do some of these other things with large language models, they'll hallucinate, or you can get them to state completely different things depending on the kind of conversation you have.
Right.
And my argument is that these failures are because of the lossy embedding of a graph into this hyperdimensional space. And it's because the large language models are trying to do something that's not natural to the structure that they have. So they're doing it, and they're, if they're large enough, I mean, there's as many, I think we've reached as many neurons as the human brain or close to it. So if it's large enough, you can really get really far along with sort of saying, well, this isn't quite how I work, but I'm going to truck through it anyway.
Large enough, and also have enough data. I mean, they're exposed to ridiculous relative to humans. So there's of course very, very significant differences right now. So this is actually a point, and I remember the point I wanted to come back to earlier about things like hallucinations, and in general, whether the current state of the art and the current performance of these models points to a difference in kind, or is it just, are we some fixes away, and we're on the right sort of theoretical conceptual path, or you're making the case that no, there's something radically different going on in the case of people? And I think this is sort of the core discussion here. You kind of you sort of detect in the kinds of mistakes they make something that's extremely not human-like. And I think anybody who spends a decent amount of time with these LMs will have those experiences where you're like, that's not just like you're missing a fact, which people do all the time, or maybe even contradicting some belief that you say you had, but now you're saying something maybe that's not consistent with that belief. But it seems like there's like who was I just talking to? You just said this. I said, don't repeat this, and then it repeats the same thing. Like, please don't repeat that, and it just repeats the same thing. Like, what on earth is going on? This is an extremely unhuman type of thing to do. I mean, it's not the best example of the kind of things you're talking about, but I think this is sort of where we're at in sort of the empirical landscape. Is we certainly do see these kinds of this dissonance, these cases, things like hallucination. Now, people hallucinate too, but it is a different kind of hallucination. I think
most of the time they realize they're hallucinating, which is really key.
So, I mean, I know people who make stuff up, and they kind of seem to believe it in some sense. That almost looks like it doesn't really matter what their actual past was. Like, this is the network's generating this now, and I don't know to what extent. I guess that's where I'm. I think there's a lot of room here for making more precise, specific claims, and maybe you've done that, or maybe you can do that. About what kinds of of hallucinations exist in the networks, in the models that we would never see in humans, and they're just of a different type, or what kind of contradictions, things like, now these three people they're siblings or whatever, that realization, and that sort of percolates to the rest of how you're gonna talk about these people and how you're going to think about them. Maybe you could argue that large language models don't do that. They can learn, you train them on some new fact. Does that successfully percolate in the way that you would expect that in your system? There's sort of hierarchical knowledge graphs, and then that percolation sort of maybe comes for free. Is like there's a central node that's connected to a lot of other nodes. You update that node, and it changes the behavior more broadly. Maybe the claim would be that we don't see that kind of thing in these models. We haven't really talked much about what it is that they're learning. If autoregression aside, what happens in these models though is that they are churning through enormous amounts of data, and what they're doing is not memorization. They're not regurgitating. People have this misimpression that what they're doing is predicting the next token based on the fact that they've seen this sequence before. That's not how it works at all. Language can't work that way because every single sentence, the combinatorics are too big. Our previous 10 words were probably never uttered in the history of humanity unless you're reciting the Pledge of Allegiance. You're not going to have the exact same. So they're not simply regurgitating what they've seen. They are doing something much more similar to this. So there's this embedding that's happening across many layers, and they really are abstracting away, for lack of a better word, what these tokens, sort of how you represent them. The word it's not just the word, and I alluded to this a little bit earlier, right? And the word, any word that you use within the model, it goes into the model, it doesn't just remain that token in this sort of very, very base sense, and it's just trying to guess based on, this is a very important point, it's not just trying to guess based on the pattern of these tokens per se, it's turning these tokens into this much richer and embedding. And with the transformer models, those tokens, the way it gets represented is combined with all the other tokens, and that's what attention is. The ultimate representation of any token, any piece of the sequence, is combined with all the other members of all the other tokens, and it's sort of structured that way. And so it's not this dumb system that we can just easily conceptualize and say it's just taking these patterns and it's producing the pattern. These are hyperdimensional representations of the original pattern in such a way that, and when it's learning, it's doing that same thing. It's not learning the sequence of tokens just like that, just the way they appear. It's learning them in this much higher dimensional, much richer and combinant, I don't know what the word is, combinatorial structured. Again, the idea that it's structuring the individual tokens as combinations of the other tokens. This is all built in to the way it's representing that information, which is why it's really doing conceptualization. It's not doing what we think it's, at the simple level. It sounds too simple. Does that end up looking like a graph? In some sense, it is sort of it's a directed graph as you go from layer to layer. But I don't think that it captures it. I think we have a disagreement. Maybe we're closer than we would think, in terms of what it is it's doing when it does those hyperdimensional embeddings, that it ends up, and it is, again, sequential across layers. It may end up being captured, sort of with a kind of graph theoretical framework. But I think we're disagreeing on whether it's sufficient. The way the LLMs are doing it will ever be sufficient.
This is a good word. I think in technical philosophical terms, you are saying we both agree that autoregression and this kind of process that large language models do is necessary for cognition.
Certainly autoregression. But what about the training of the model, where you're determining the weights in the transformer model? That's this embedding, right? There's embedding plus self-attention. But the embedding happens with self-attention. It's churning through the whole thing. So it's doing the embedding such that it's going to be good for the combinatorial self-attention mechanism. This is very, very, very abstract, complex stuff that's going on. It's not just, simple, so it's pattern match. Could that be sufficient to capture the kind of knowledge representation that you're rightfully pointing out? Certainly we do. Now, does the fact that there are deficits now in the current system say that no, it's doing something radically different? You would say, maybe make that case. You have other ideas of how you can do it computationally that you say are inherently absent. First of all, are we sure that whatever it is you're envisioning isn't actually sort of epiphenomenally happening in the entire embedding, layered embeddings and all of that?
Well, I think I'm actually sure that it is happening. I just think it's happening in a lossy way.
Okay.
And so.
So maybe our point of contention is it may not be that large. So what do you mean? So lossy as opposed to?
I think there's all sorts of interesting things about how you can represent each neuron as a hot field network and other things you can transform neural networks into. But I think what I'm saying is that I think you have to have some kind of knowledge graph structure for memory and knowledge and things like that. I'm saying I think the large language models have some kind of knowledge graph structure.
They do.
Sort of embedded in the neural network. But what I'm saying is, and by the way, the reason we keep talking about deficits, we're talking about really clear ones like hallucinations, but some of these deficits are like fundamental reasoning capability. So this isn't just an academic pie in the sky conversation. This is like, you know, there's reasons our robots aren't smart and can make mistakes and shouldn't be performing surgery or
No, and hallucinations also.
Sure. This is an important conversation.
Very important. It's like maybe the most important as far as these models go is are we getting to like utility where they can do the stuff that we want them to do reliably? I agree. It's a very, very fundamental.
Yeah, absolutely. So I think so I guess what I'm saying is there's two systems, and there's sort of the more graph-based system, and then there's the autoregressive system. And we've built an autoregressive system that's large enough and that's been fed in the entire internet that it's sort of bodged together the second system that it needs inside of its hyperdimensional embeddings. And so I think somewhere in there you would find something like a knowledge graph that's embedded in.
So I want to stop you real quick. So, you know, when we say it's an autoregressive system, and it goes back to the software kind of a point, well, maybe not exactly software, but short-term memory and long-term memory. The training regimen, it is trained to do autoregressive next token generation. But in the process of doing that training,
yes,
it is forming this very, 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 very rich, hyperdimensional, all of that, sequential, we could even say it's a graph. Representation of all the information in order to do the next. So the autoregression is sort of the task, and it's the environment in which it produces. It's able to perform its behavior. I think it learns to do the autoregression, which is in other words, it is fundamental, but at the same time. That doesn't limit. Yeah.
Everything you just said about these are doing something that's not just next token prediction is something we agree on. By the way.
Well, no, but I'm saying it is just learning to do next token generation. But to do that, it's got to learn about the whole. It's got to learn about the world.
I see what you're saying.
And so it needs, and we see that that's why it's so surprising on some level. I kind of remember when I first I learned that that's what they're doing. I was like, that can't be right. Like I thought somebody made a mistake. Next token, what do you mean? Like how could that encapsulate and contain within it all the information? You know, how could that be the key? But the answer is that in order to generate next token, you've got to organize your knowledge of the world sufficiently that you end up learning concepts. You end up, it's still just next token generation is what it's learned to do, but the trained network, which is why so the brain, I think it was like long-term memory is just the trained network. This is how I think of it. Right, the trained network is just it's a set of weights, right? And the set of weights at this moment is just some system that if you give it a certain input, it'll produce an output, a single output. That's the brain. It's this trained network. The process of cognition is that trained network in an autoregressive environment, so that when it produces the next token, that's fed back, and then it proceeds from there.
I see.
But I'm not really making a strong. I am making a strong statement about how the brain gets to the state it does, but the state itself, the weights, can contain within them all of this richness that you're talking about. So it's not a limiting factor to say that it's autoregressive. That's the environment in which it produces, and that's what it's trained to do. But what you get in the end is a very rich, representation of all of the information that has been fed in order to learn how to do that next token.
So I think we might actually be agreeing here.
Are we going to hug at the end?
I think we might be agreeing here, which is that in the process of doing the next token prediction, it learns to simulate the whole system. And what I'm talking about, and what a lot of cognitive scientists besides me, by the way, would say is a sort of almost two systems that interact with each other. It learns to have both of those systems, sort of the generative part of the system, and then also here's a stored knowledge graph and here's stored knowledge.
So I'm saying there's one system. Right, I think I'm claiming that it's one thing that just operates just like the Elan operates in this autoregressive environment. But you're saying there are two systems. Are we disagreeing? Let's get to the point.
So
What do you mean by two systems?
Transformers are universal function approximators.
Sure.
I'm saying there's two
Neural
systems.
networks in general are
Yeah. So universal function approximator just means if you have a big enough one and enough training data and enough training time, you can approximate any function.
So it's a Turing machine or whatever.
Yeah, to an arbitrary degree of error.
Nobody thinks the brain is a tape with the lead head moving back and forth. You know, it's
Exactly.
the fact that I find that an interesting point, but I'm not sure that. Yeah, but go on. Sorry.
So what I'm saying is, at its heart, cognition, as we think of it, is a two-system process where you have one system that's sort of autoregressive, generative, in the same way that transformers and transformers are able to do this very naturally, because fundamentally that's what they are. There's a second system which is a more static system. It's something like a stored knowledge graph, and then a lot of what we think of as cognition, it's taking things out of the second system, putting them into the first system, doing some transformation and putting them back into the second system. And so you've almost got like a warehouse, and then you've got a guy that gets boxes out of the warehouse and he works on something and puts the box back in the warehouse.
Got it. Okay.
And so what I'm saying is, I think because transformers are universal function approximators, they've managed to capture both systems to some degree, because they can capture graphs, and you can lossively, but you can embed a graph into a hyperdimensional space, which is what transformers are. But what I'm saying is that they're not capturing the second system, this graph-based system, very well, and that the fact that
And that's why they make the mistakes.
and that's why they make the mistakes they do, and that the second system is really, really, really important for a lot of advanced reasoning capabilities, especially reasoning over very, very large amounts of information. So I think a perfect question that it's really hard to get large language models to do, even if you hook them up with RAG, which in some sense, if you do that...
I want to talk real quick. What's RAG?
RAG is where you... By the way, I think this might be a point towards me. RAG is where you give the large language model a second system that stores information. And there's a lot of technical detail there, but essentially you give it a second system that stores information, and you can take information out.
By the way.
It does. I'm working on that.
I certainly can't. I'm not going to hold you to account, because RAG in its current incarnation, it's like 6 months old, a year old. I don't know.
Yeah.
I'm kidding. That's not really a point for me.
But it works better for a lot of things than a large language model by itself, I think. And I think that's the important statement. So RAG is where.
Well, okay. So I think that's a great point to jump off of a little bit. So why do you need RAG? And the reason is there's two ways to get information sort of into. Well, now I guess there's three. Right? There's three ways to get information into a large language model. You can train it, which just means you're updating the weights. That's sort of the brain that I was talking about. That's sort of the static system by virtue of here's some text. Here's what you should generate based on that text. It just like any neural network, it will try to guess based on here's the Pledge of Allegiance. Never seen it before. What should the next word be? I pledge allegiance to the. It's never seen it before. It doesn't know. I pledge allegiance to the God. I pledge allegiance to the. But then you say no, it's flag, and now it's learned it. And now next time it comes through, it will get the right output. So that's training, and you've changed the weights. The second way is you can do it in context, meaning when it's having the conversation, it's going to learn, it's quote unquote learn, but it's going to go into this context. It's going to go into its inputs as it's going along. That's how you can tell a large language model, hi, my name is Elan, and it'll say, how's it going, Elan? It's not that it's that name. It's not taking. It's not taking that fact and put it in some other stored knowledge base. It's just in the context, and in other words, it's just part of the input that it's going to keep autoregressively going through. That's number two, and then number three is kind of the stuff that Daniel's talking about, where you can have a knowledge database that the language model can try to access. Now, it's the autoregressive system isn't really doing it. You have to have some other process, and retrieval augmented generation is one of them. Augmented here is, so the generation is just autoregressive generation. The augmented is that you're taking the current whatever the input is, and you're saying based on that, I'm going to go look up and see what might be relevant in some other database. And it's a distinct, separate process. And I think this is the key. Is why I elaborate on this so much. It's sort of the key of the debate. Is there knowledge stored externally to the sort of trained model, and then the trained model goes and retrieves it, or I don't even say the trained model, it's not the trained model retrieving it. There's some process that goes based on whatever's going on in the current conversational context or thought context, says, let's go retrieve information from that other thing, pull it in, and use it. Right? That's what retrieval augmented generation does. You're saying, yes, there is this other database that has to be accessed. I'm making it's maybe a devil's advocate argument, but I don't know. That doesn't need, it's all the trained model, and that what knowledge representation is, it's when we consolidate and when we're dreaming and sleeping and whatever, all of this is just a way of training the model. It's really just a training process rather than an external separate. Now, do I think that training process leads to exactly what LLMs do? That's not the claim, right? In other words, I don't know what the structure, and it's not a claim that the particular transformer structure is the right representation, but in the end, it is a substantive claim about what you have as a trained model, rather than something that is a trained model plus an external representation. And that, I think, is the point of
I think that's the crux.
That's the crux.
Is it a two-system or one-system process? Because I think we both agree that system, the autoregressive system, is important. And very rich and complex and has sort of conceptual knowledge, right? Yeah, it does.
All of that stuff. Okay.
Yes, I think we completely agree on that point. My point is that you still need this other thing. So the autoregressive system is necessary but not sufficient. After an hour of talking, I think we figured out what we were arguing about.
That's fantastic. We should let's scrap that whole thing and let's start from there.
It's record time for us, by the way. But
okay, now we have to fight about it. But honestly, I don't know that I have that much more even to say substantively about who's right here, except maybe I call it an article of faith. To me, it seems like the brain is just one thing, and it's just a big fat neural network. And I think that given that we have a glimmer, at least, of a system that seems to do the whole knowledge thing, maybe poorly right now, but well enough that I would say I'm going to go out on a limb, on a sort of theoretical limb, and say, let's pursue the theory that it's just single system. And then I put the ball in your court and say, no, you have to give me the argument as to, no, everything I see, tells me that there's substantive reasons to think that it's the wrong direction.
By the way, Elan is saying that the brain is just one thing because neuroanatomy as it stands sucks, and the divisions we make in the brain don't work very well. But it's worth mentioning that, in my opinion, this is also something we disagree on. I think the brain is a few different things that have sort of
and I don't really disagree. Of course, there are nuclei. There's these clusters that do stuff.
There's peduncles that are sort of highways between the separate portions and
correct.
Like these. And so it's worth mentioning that Elan's making a controversial claim there, that the brain is just one big ball of fat.
Well, I mean, it is, except there are. It's just that its topology is not simple. Meaning you have dense, closely, highly connected regions, and then, like you said, sort of pathways to other regions. And so the topology, it is a network, right? It all is connected one way or another. Correct. And there's certainly directionality, like things go one way, not necessarily the other. And so it's a graph and all of that. So again, I don't know, that claim isn't really a controversial one. It's really more conceptually, does labor get divided up in such a way that this model of just next token generation, even though it's recruiting all these different systems, isn't really an account. Like computationally, it's not the right account. So biology sort of aside, like yes, it's almost hand waving to say it's one big network or it's not. Even large language models. Also, there's all kinds of sort of fascinating topology that happens sort of semantically, even though it's all just the connection. But the connections get zeroed out. I mean, a lot of it's just not meaningfully. In some ways, things are not always uniformly connected, and there probably is interesting topology there too. Of course, it's not as simple as just saying it's all just one big brain. I'm not making the sort of the very simplistic version of that argument, but computationally, are these things being recruited in a way that's captured by what a trained network doing next generation or not? And you're saying no. There's a different computational process. It has to be described differently. It's not just a multifaceted trained network.
And you have to have this other process.
Right.
I think that's sort of our core disagreement. It's worth mentioning your idea is more parsimonious. It has less moving parts.
That's why I think
means that until you're proven wrong, science is really on your side. My intuition is that this is wrong, but as a scientist, I have to go out and prove it, and I'm working on that.
Well, I mean, but on the flip side, you can point to deficits in these models, as and let's face it, it's sort of subjective. It's kind of a gut call.
We don't know how to do science on these things yet.
Not even close. and when we're in absence of really any science of it, what we can say is like, I could make the claim that it's just a matter of time and improvement, and you could say no, it's never going to get there on this current trajectory, and we can't really resolve this except empirically, and that's why science is cool, because but I think it opens the door to like, this is an interesting debate. And I'm not just self-servingly saying yes, this is an interesting debate. Like, no, I think this is something that research hopefully can certainly on the engineering side, people want to solve problems like hallucinations, and maybe you have insights that can solve those problems, and you're saying this is an engineering solution. I'm also saying, and we're both saying, this is also, I think, a question that has potentially very large importance to understanding humans and our brains, and I think those are both true in the sense that this both presents an operational, practical question, and also a theoretical, basic science question. I think we both need to go back, get into the lab.
Yes, we do, and I think
we're in the same lab, so we're going to pursue opposite, and that's perfect. I think that's
great. That's science.
Yeah,
we both go poke at reality and see who's right.
Yeah,
that's what science is.
I think if we, the next conversation or more of this conversation is, what can we do now besides just say let's keep trying to improve on, in the current models, or you see a radical departure. What can we do now in the current space? Like, what would be good tests of sort of your theory or my theory that we could say, it really lends evidence. Like, I'm not claiming like that if we just keep training them in the current, with the current architectures, although it may be the case, maybe, we haven't seen GPT-5. We haven't seen what these things look like with the scaling laws may end up solving the hallucination problem. Apparently, certainly got a lot better. Hallucinations have gone down a lot with newer models. Maybe I'll just sit back and be like, let's see. But are there things we could do now experimentally where I would say, look, if we fine tune it, here's some new information. We're going to give it to the thing and we're going to train it on that information. I would expect, according to my theory, for things to work out, but according to your theory, to work out differently. Like your case of the siblings and stuff. Is there something that your theoretical framework would predict in the case where you give it certain information and you fine tune it, where you would predict a hallucination, or you would predict a kind of a mistake because it doesn't have access to the database, whereas I would predict, no, it should not make these kinds of mistakes.
Yeah, we should have that conversation.
Yeah. I wish we could do that for the next couple of years.
Oh my gosh, that would be great.
Okay.
In a dream world.
If anybody wants to, anybody wants to write a check to support Daniel's next couple of years of graduate school, then we can focus exclusively on this. That would be helpful.
Yes. Yeah. Please do.
It can be. I think it can be astonishing to realize.
This is it.
That this is what's doing all of that stuff.
Yeah.
And then even more astonishing if you buy that that's what's, even knowledge aside, right? That's sort of at least conversational language use and stuff is enough. But yeah, I wanted to get into working memory because I don't think it's memory at all. I think it's just the autoregressive loop.
I agree, actually.
You do?
Yes.
You want to write a thought paper on this? Because I've been meaning to. I want to say working memory is not memory. I want to put out a paper basically that now we know that like I think that this is an insight we now have, that autoregression works so well in the linguistic case that there's no reason whatsoever we should posit that anything besides that is happening, and that the reason why you can recall stuff is because because it's non-Markovian, because you have to, so the brain has to encode the previous few states. That's the state has the sequence, and all we're doing when you do these working memory experiments is we're just tapping into the fact that it's there, but it's not for the purposes of retrieval. That's where the cognitive science got it wrong. They thought this is for retrieval. It's not for retrieval. It's just the fact that there is activation. There's that in the brain has to retain that information in order to do next token generation, right? But it's not so you can then repeat it. That's like an epiphenomenon that happens to work. And then stupidly, I'm sorry, I mean, I think it's dumb. I think they're like, because nobody ever gave a good explanation of why would you do it? So you can remember a phone number. That's what? That's why we evolved this. That's how this core function. There's a core function of our brain that's
maybe the core function.
Maybe the core function, right? Of the cognitive core function. I mean, breathing's good too, right? All that stuff. But yes, so the cognitive core function is you can remember a phone number. That always seems suspect to me. Like it never was clear why you'd want to go and retrieve, like explicitly retrieve. So I don't think the explicit retrieval is the point at all. I think it's a indication, it's good evidence that we do retain the previous sequence up to some extent. I think the drop off in accuracy in retrieval, I don't know what it means necessarily, because the explicit retrieval is not the point. So I don't know if you really are forgetting the sequence in terms of like for next token generation, or it's just that the retrieval process, this explicit retrieval process, which is some sort of weird clue like that we're able to do, but isn't really the core function, may just drop off. I don't know. And it's an important question for me, because can we use all of that? Is all of that cognitive science useful? I don't know. Like the drop off is an important fact, but is the nature of the drop off I don't know if that really tells us anything about like how the sequence, the context is being updated, like, you know, and being degraded. I don't know. I'd like to think that to 50, 60 years of work, I'd like to think we can go back to it and be like, oh, now we have insights about how the brain is representing the sequence for next token generation. But I'm not convinced.
You'd be really interested. My kind of mentor as an undergraduate, Dr. Anders Ericsson, he worked on a bunch of the really foundational work on working memory.
Really?
He was older guy. His mentor was, his advisor was Herb Simon.
Cool.
And so
MIT.
Yeah. The kind of
there's cognitive science.
Cognitive science. And so he did a bunch of the foundational work, and I remember I talked to him when he was older, obviously, and he was really disappointed that people had adopted the ideas that him and some of his colleagues came up with so well. He said, we were scientists, we were coming up with the best ideas that we had
at the time,
because that's what you have to do as scientists. And he said, and I'm proud of that. I don't have, I don't have.
But he's not so proud of the people who came after, like
who he
like
told,
they should have done better.
Yeah, who he told, hey, here's the theory, and they said, oh, okay, that sounds good. And he was really,
it's awful.
He was really disappointed that in like 30 or 40 years since he had come up with these ideas, nobody had come up with anything better and really poked holes in his idea.
I think the big problem for cognitive science
that's what makes him a real scientist, by the way, that he was disappointed that people weren't disproving his theory.
I love that story. I think that's awesome. But I think the problem with cognitive science, certainly, at least the cognitive psychology end of cognitive science, is that you're sipping through a straw. Like the kind of data you can collect, it's just so constrained and limited that what ends up happening, what I think ended up happening, is people built theories, and it's sort of like looking for your keys where the light is. People built theories out of what they could observe. And what can we do? We can read people's sequences, and they can recall those sequences, and you can measure it. And it's highly measurable, and we can there's empirical data. This is the behaviorists kind of impact. Don't tell me about your highfalutin abstract theories. What can we measure? And they were constrained by what they can measure. And you end up with something like there's a core function of the brain to retrieve because we can see that people can retrieve. But maybe it's just because that's how something you're able to measure is retrieval. And maybe that's not even a core function at all. That's sort of my claim. And I think maybe this is true for a lot of cognitive psychology, that you end up, unfortunately, because of the limitations in the kind of data you can collect, you end up building theories out of that very, very narrow, limited kind of data. And I don't know that there was a better solution. I think now we've got computational models that are able to do this stuff. It's a different way of doing, cognitive science always was supposed to also be doing, but the computational stuff didn't work. The architectures, the AI architectures, good old AI, all of it, to some extent, didn't quite produce. The connectionism, parallel to PDP, whatever, ended up becoming neural networks, turns out to have worked to do some very significant portion of what we call cognition. And I guess the argument could be like, that's okay. So that was necessary. Everybody had to pursue these different. But I don't think. But I guess what I would say is, like, I think there's textbooks filled with, which are probably, including my own textbook, filled with wrong information, making claims about boxes that maybe don't exist. In these, so long-term memory, short-term memory, working memory, or it was working memory as sort of a memory system. I think that needs updating. I think maybe the conclusions that were drawn need to be updated based on new facts and have come to light. New information has come to light that call into question whether these were inaccurate. There were actually mistakes made. I don't know.
Yeah. I think. I think there are boxes, but because large language models are a giant universal function approximator, and because they have all of this data, they managed to simulate those boxes within the large language model. And
so, right, our debate is whether it's one box or multiple boxes, but you may agree that the particular boxes that cognitive science has arrived at may not be accurate.
100%. But I think, large language models are really smart and they're very impressive, but if you gave me the brain the size of a warehouse and gave me 1,000 years to read the entire internet, I could beat the pants off a large language model.
But they're going to get more, if they are getting more efficient all the time. There's some spectacular, much, compared to the number of parameters you needed, a year ago, and some of these lighter, and by the way, open source models that are like a few billion parameters. They're much smaller, and they're beating benchmarks. So maybe we'll get to much more efficient. And the training regimens also, it hasn't been much of an area of research. I mean, at least I don't know what's going on the industry side. I think there's potentially a lot of work that could be done in training these things in a more sequential way. Like right now, we don't do it the way we do with humans. Maybe they should start out with simple stuff and then build up to more complex stuff. Maybe that would lead to a faster, and you don't need as much data. But the computer's cheap enough, and people don't really care. Like if we get to that model, they only care about inference. If everybody just wants to get to the model, the best model. And they don't really care about, they're throwing ridiculous amounts of money and compute. And then once it's done, it's done. And they're like, okay, they're not worrying about, right now they're just scale. But in terms of explaining and trying to replicate what humans do, which doesn't require, what are the equivalencies, like hundreds of thousands of years you would need to spend as a human being going through all this data. And of course that's unrealistic. But from a scientific standpoint, maybe the engineers don't care. But thinking about how people are able to learn so much and get so good with so much less data, of course, is a critical question, both for just language use, but knowledge, all of this stuff. And again, maybe you would say that it's because we do it completely differently. I would say maybe not. A difference in qualitative, just a quantitative difference, or a better model with a better training regimen. Maybe we could end up doing something like we see with humans. And there's also, we don't know what genetics is doing. We don't know what the structure is, like how much knowledge may be in there to some extent. I mean, I don't want to quote Chomsky too hard on this, but because I think he's a guy, I think he's wrong. I think grammar, syntax, it's wrong. It's like, now we know. You could do language production without syntax. You don't need, it's nothing to be explicit. It's not in there. It's just not in there. It's implicit, but that's epiphenomenal. Whatever. We can get into that. But he is right in the sense that there's not enough data. Children don't have enough data to learn the rules. So there's some sense in which perhaps these rules, remember, they're just weights. right? Whatever is when the model's trained, you're just training the weights. Maybe in the process of with genetics plus developmental environment plus stuff that's happening in the womb and all this stuff may give you lots of scaffolding that makes you ripe for language. That's before you ever truly encounter language. So it's not. There's room for lots of other stuff besides what we think of classically as training a model.
There's a meta point to be made here about AI research, which is that all of this work may already be going on, but AI research currently, because it's the biggest economic thing in the world, is in the same place that finance research or defense research is, which is the really good stuff doesn't get published because you don't want other people to know about the really good stuff.
Right. That's my deep-seated hope and fear at the same time. Like, maybe we'll never know about it. Maybe it's just like, boom, my model can run on a thumb drive, and I'm not telling you how. It's like, and it's able to do all the stuff, and you can put it in an edge, and it works, and we'll never find out. And it turns out, you solved like the problem of cognition, in a deep way, like that tells us about humanity, and we're never going to find out
because it makes enough money.
and absolutely, and as much as open source and all of AI and the progress has been a product of the fact that there's a tremendous amount of sharing and collaboration. That the open source kind of ethos has been huge and critical. But let's face it, OpenAI is not open. And we don't know what their models are. We don't know how they work. We can only try to draw certain very coarse inferences about their scale. You can try to follow, as some people I know do, like GPU orders, how many H100s are shipping and things like that. But you don't actually find out what tricks they're using. And I agree with you that there very well may be these kinds of things are happening and insights are taking place. But science for science's sake and basic research, there's not really an incentive or motive for the industry to care how humans do it on our wetware, which has all these other constraints and doesn't have to operate under the same conditions. Like maybe they just don't care.
Yeah. If there is economic incentive, that would be other concerns that I would have. But
yeah. Let's not get into it. I'm sure. But unless they think that there's tricks, there's secrets that the brain has, and they want to steal them. But frankly, their job is not to figure out how the brain works. And therefore, if there's a direction they can go in that just seems to yield fruit that doesn't reflect how the brain's doing it, they shouldn't care. They to use the modern parlance, they're beholden to their shareholders, right? Although OpenAI is not publicly traded, but they're the organism.
They're beholden to Microsoft.
They are very much beholden to Microsoft and other investors. That's true, and they're beholden to their organization, right? They got to stay up front at the top of the pack, and they have to do whatever and they have to put all their resources into that. They can't be worrying about, well, is this how the brain does it? But what about humans? They don't have time for that shit. So I hope that that there's people whose concerns are maybe different than just engineering the best, most efficient and economically viable model, have an opportunity to plumb these depths, and I hope that they're able to do that, and I hope also perhaps that whatever happens in an industry, can percolate out at some level. There's a big concern I think we all should have, that science and academia itself is falling off the map in the sense that the progress is all happening in industry, and that means that the insights may be closed off from us, because they're privatized, and they're not asking these kinds of questions that I think basic research people who are interested in neuroscience, for example, would want to ask. And so what's the solution to that? Well, I guess more public funding. That's not exactly seems to be the climate right now.
And public funding isn't really funding these types of things either. You and I both know public funding in neuroscience is extremely clinically focused.
Extremely clinically focused.
Which is understandable. So I should say I'm not against the people that are doing this, because the people that are giving out this funding is the National Institute of Health, and it's completely reasonable for the National Institute of Health to be clinically focused.
Yeah, just a quick aside. So Daniel and I are on we're on a grant we won't get too much into it, but it's trying to predict or to detect psychoactive substances that are emerging and stuff. And there's somebody from the NIH who sits in every meeting, and often her role is to say, okay, what are the health implications? What are the public health implications of this? And that's NIH's mandate.
Good.
And I applaud that. I applaud that.
If my tax dollars are going to the National Institute of Health, I want them to be health focused.
Correct. However, basic research, as we all know, has yielded extraordinary results that have had health implications and human focused implications. And it seems like this is a moment in time where there's really some very powerful, important insights into the nature of language and probably the nature of cognition and all of that. And I would hope, and I personally, I guess advocate, if for lack of a better word, that basic research and so research for the sake of understanding human cognition in this particular time period should really be, it has to be boosted. Like, we can't let industry just walk away with this thing and not learn what we could possibly learn, because we don't know what are the possible implications, right? For health, for understanding ourselves, understanding how the brain works. Does this have implications for? Here's a good one, right? Alzheimer's and memory loss. I have some things to say about that, and I don't know. I don't know if they're true or not, but that are strongly influenced by these conversations, the things we're talking about, like autoregression, like and the memory and the fact that you need to maintain that sequence, right? I think there may be some very core insights if we understand the brain this way, and if we could substantiate that the brain operates this way, that could have real implications as to understanding the nature of memory loss. What is sort of the computational basis of dementia? What's going on at sort of this level? Do we have substantive things to say now on the basis of that? If we have a theory now of how cognition operates, and it involves, in this case, the ability to maintain a certain fidelity, a certain degree of fidelity of the previous sequence that happened recently in memory, if we kind of buy that the architectures that now work computationally in, say, LLMs may actually yield some real insight into how it works in human brains, then maybe we will have something substantive to say about something like dementia. And it's not neuropharmacological. It's not saying that it's not giving the cellular or molecular basis for it. It's computational, but that doesn't mean it wouldn't have broad implications for how once you understand it this way. If it gives you insight into understanding what's going on, that could of course have implications. Let's say it's about brain regions and how those brain regions are talking to each other. Where is the breakdown taking place? That could of course dictate and inform how you might design a drug to target these deficits. So I think the health implications, the sort of human-focused implications, it's not just knowledge for knowledge's sake. It's not just sort of computational philosophy, which personally I think is important. As a species, we do want to understand ourselves too. But I think it behooves us as a society, even if concrete results and sort of health benefits and societal benefits are what we're throwing our money into, and I think that is very reasonable to say that that's what we're going to put tax dollars behind. I think that this certainly could yield these kinds of investigations are potentially very important.
Yeah, and I think it's worth mentioning, and this is sort of a central point in my dissertation, because in my dissertation I'm using large language models to help people build better neuroscience theories.
Yes, right.
And it's worth mentioning that neuroscience research, and all scientific research, but neuroscience research works like a funnel, where you have what are called computational neuroscientists who come up with an idea and they test it on data that's already available. So they just say, here's the state of how these neurons connect to these neurons, and I'm going to run my theory and see if my theory plays out how I expect it to there. And then some percentage of theories get knocked out at that stage. But the good theories make it to the experimentalist, and the experimentalists have rats and flies and all sorts of other things. and they say, all right, well, we're going to test this theory in a more experimental way, and here's how you would falsify this theory, and we're going to do an experiment. And then some of the experiments don't work out how the theory predicts, and so you throw out some amount of things at that point, and then the experimentalist pass things off to the clinical neuroscientist, and the clinical neuroscientists do further experiments, but experiments that are more focused on, all right, well, if the brain works this way, then it means Alzheimer's works this way, and it means if we do this, we should be able to help Alzheimer's. And so they'll do some sort of experimentation, really focus more on an application like that. And some of those things don't work out how the theory predicts, so more things get thrown out then. And then finally, you have sort of clinical trials, which the FDA is involved with, and that's where things are really, really tested rigorously before they're used on humans, and some percentage of things are thrown out then. And so you have something like a funnel where theoretical ideas about the brain get thrown out at each stage. And by some napkin math estimation I've done looking at sort of the stats of how many theories make it to experiments and how many experiments make it to clinical neuroscientists and how many of those make it to clinical trials and how many of those actually make it into real products that help people. I estimate that if we're able to build theories, so do this sort of fundamental work, if we're able to build theories that are 5% more robust, then we're able
computational, like on the computational.
On the computational side, then we're able to double the amount of effective clinical trials.
Cool. That's awesome.
So that's huge. That's having the time till we find a cure for Alzheimer's and Parkinson's and all of these other really important things. But the work that the computational neuroscientist is doing at the beginning of this process, he's not necessarily talking about anything clinical. He's not talking about Alzheimer's. He's not talking about Parkinson's. It sounds a lot more like the conversation we've been having. And so that receives less funding. But actually, if you give a small amount of funding here, the other nice thing about computational science is it's cheap. You don't have to buy equipment. So a very small amount of funding here can have an outsized...
Dennis, cheap, guys. Just send checks to...
But a very small amount of funding here can have an outsized impact down the road.
I think it's a great point, but I want to. So there's something about this moment in time where the computational theories. So historically, and I don't want to throw shade on the computational approach because absolutely necessary, and as we've discussed, you don't know where the insights are going to come from. However, historically, most of computational neuroscience, like Fitzhugh-Gomon, and these models of spiking neurons and all this stuff, they didn't do much. They tried to replicate certain kinds of sort of low-level dynamics that we observed in the brain. The models now, some of them anyway, right? These, at least like the LLM models, but also in general neural networks, they actually do the thing. They do the thing, the behavioral thing. They go all the way in some ways to behavior, and so it's much easier in some ways to make the case now that these computational models have, first of all, that they have these implications, potentially, but going back to your sort of point of like the robustness and the likelihood of success, I think there's an environment now in which your likelihood of success should be higher if you're working within the domain where you can actually see, does it do the thing? Like, can we get, I think we're gonna get to the point probably fairly soon, with robotics plus AI, where you're going to be able to test these fruit fly models in a synthetic fruit fly. It's going to do the thing that fruit flies are supposed to do, or you can lesion it in ways that simulate a lesion in a fruit fly. And so, as the models get more and more powerful, as they surely are becoming, I think the argument becomes much stronger for investing on the basic research side, computational models, not with the clinical end in mind, but at least a behavioral end in mind, something that's close, not just simulating some process deep within the bowels of the brain, but that actually inform some outcome that in some ways looks similar to the outcomes we care about. Things like, whatever, navigation, whatever it is your fruit fly, or memory, learning, whatever the fruit flies do, or that people do. I think this should be a golden age, and again, we need to invest for it to be a golden age, but a golden age of computational neuroscience, computational research, with these kinds of possible human-focused human positive outcomes.
And there's things that have happened just in the past 5 years that I think have gotten computational neuroscience to this point where it's a really exciting time to be in it, where we've gotten the complete connectome of the adult fruit fly. Every single neuron, how it connects to every single other neuron, that's huge.
You should do a dissertation.
Yeah, I'm doing a dissertation on that. We've got a complete map of every single cell in the mouse brain.
Right.
In the past 5 years.
Right.
We've got the first clinical tool that uses these connectomes, human connectomes, to sort of assess, all right, where is the damage to humans? We've got a huge project working on getting the complete mouse connectome that I expect to wrap up within the next 5 or 10 years. We've got
You need to finish your dissertation before that, though, just so you know.
Yeah. I'm working on, we've got more genetic information about the brain than we've ever had before. I mean, the amount of data that we've got that you can test your theory on and sort of have a synthetic fruit fly is enormous. So, this is an exciting moment to be in computational neuroscience.
Yes, and just the additional factor that at least some forms of computation have really proven to be like models.
Yeah,
it seems of the real thing. I think should put the wind in the sails of computationalism in general. Not necessarily the classic computationalism of what cognitive science historically did, but it's going closer to neural networks, where you're building systems that can. I think one thing we've get the human conceptualization can sometimes be a little bit of a red herring or a garden path. I think that's we don't need to be able to it's not about conceptualizing it externally. We may just be able to do it. Building smarter machines in the way that we now know to do, data plus architecture. And that's not sort of the classical cognitive science perspective of computationalism. It was about theorizing about what the architecture was. Now we were like, I think in some ways it's a healthy shift is to say, let's just try to finesse the architectures.
Yeah, build something that works.
Build something that works. And then figure out after the fact, okay, what does that tell us? Like in the case of LLMs, in some ways, it wasn't because, I don't think people said, autoregression seems to be the way humans do it, and I'm proposing that, and therefore let's build it this way. Instead, it was, what can we get a neural network to do? Predict the next output, and then what if we do it this way? Boom, it worked. Lo and behold, that ends up being a pretty, very, very similar to what you expect people to do. We kind of think sequentially, and we talk sequentially. So yeah, maybe get the smart people have to take a step back. Like, don't be too smart, don't be too clever about thinking that our brains are going to sort it out theoretically, and instead really kind of lean in on sort of computationalism, as the approach, as almost like engineer our way to these solutions, but with a basic research kind of mentality. Yeah. Thanks. That was a really cool and interesting conversation, and I think there's something really kind of meta about this, which is that in the process of talking about stuff, I'm sort of running these autoregressive models and reasoning through something we haven't talked about. Sort of like the chain of thought and this kind of reasoning processes, how that it lands you in a different spot. And coming back to your point, I have a different model now. By virtue of these conversations, so there is clearly this dynamic that's happening. Even though I think it's one system, but it's one system embedded in the world and in a conversational context that's going to get fed back. Like next time we talk, even if it's a week from now, we're not going to be mid-conversation. But I'm going to talk about this, and not just with you. I'm going to think about this differently going forward. So there's this very cool kind of process of certainly informing and updating the model through these conversations. But conversation as thought is sort of one of the key foundations of like this whole perspective. That's what we're doing. It's not all in there. The information's not in there. It's not in the model. It has to do this stuff. Get it out of its model. Get it out of itself. work through things, and then that ends up getting fed back into the model to retrain itself. So it's all very odd, but it's sort of a wonderful, this was a sort of a wonderful kind of demonstration for me of that process.
Yeah, absolutely. And this is the really cool thing about being a neuroscientist, is you get to use the brain to study the brain. And,
Amen.
And that's a unique place to be. Well, you can find me on Twitter and Substack, and then I have my own website. I'm also on Blue Sky, because I know people are leaving Twitter in droves right now.
So now I'll show my age. My socials are much less developed, but I do have a website that's kind of rudimentary on Barenholtz.ai. I have a Substack, which I have to populate with more stuff. But if you check it out, and I know you're visiting, that'll encourage me to do a better job on the social side. So please encourage me to do that.
Oh,
like and subscribe. Yes,
this is an awesome channel. He's having lots of conversations like these on here.
Oh yeah,
you should like and subscribe.
I love this channel. I have to skip over the interviews with me. I don't look at those, but I love to watch the other stuff. It's a great channel. So like and subscribe.
Absolutely.